Welcome, everyone. Thank you for joining me today. I'm excited to introduce our topic, mechanical design calculations and selection for office engineers. Today's focus is on connecting theory with practical application in MEP design. We will look at key formulas and examples to help you understand how to make effective design choices. Let's get started and explore how these concepts come together in real-world scenarios. Let's take a closer look at the cooling load calculation using the ASHRAE method. The key idea here is to determine how much cooling capacity is needed to maintain a comfortable indoor environment. The primary formula we use is Q equals 1.08 times CFM times delta T, or alternatively, Q equals U times A times delta T. Q represents the cooling load in kilowatts, CFM is the airflow in cubic feet per minute, and delta T is the temperature difference between the indoor and outdoor air. The other formula involves U, which is the overall heat transfer coefficient, A, the surface area of the building envelope, and again delta T. For example, consider an office space of 120 square meters. Using this method, we estimate the cooling load to be about 18 kilowatts, which is roughly equivalent to 5 tons of refrigeration, or TR. This calculation helps us size the cooling system appropriately, ensuring efficiency and comfort. So, understanding these formulas and examples is crucial as we move forward in designing effective HVAC solutions for various buildings. Let's take a closer look at duct sizing using the velocity method, as outlined by SMACNA. The core idea here is to determine the cross-sectional area of the duct based on the airflow rate and the desired velocity. The formula we use is simple. A equals Q divided by V times 60. Here, A is the duct area, Q is the airflow in CFM, and V is the velocity in feet per minute. For example, if we have a system with 2500 CFM, we can plug that into the formula. Assuming a typical velocity, say around 400 feet per minute, we get a duct size of approximately 600 by 400 millimeters. This method is really useful because it helps us balance airflow and pressure loss, ensuring efficient system performance. It's a practical approach that connects the airflow requirements directly to duct dimensions, making sure our designs are both effective and efficient within the overall HVAC system. Now let's look at how we calculate and select the right pump head for our system. The formula for the total pump head, H, consists of several components. First, we have HS, which is the static head, basically the elevation difference the pump needs to overcome. Then, H represents the dynamic head, related to the velocity of the fluid. Next, we include HF, the head loss due to friction in pipes and fittings. Lastly, we add the sum of the velocity head losses, which is the sum over all components of the K factors multiplied by the velocity squared, divided by 2G. Once we have the total head, we can determine the power required, P, using this formula. P equals the flow rate Q times the head H times the specific weight gamma, divided by the pump efficiency, eta times 102 to convert units appropriately. To make this concrete, let's consider an example. Pumping 65 cubic meters per hour at a head of 22 meters. When you run through the calculations, you find that this setup requires roughly a 5.5 kilowatt motor. This example highlights how these formulas directly inform us about the motor size needed, ensuring that we select a pump that's efficient and capable of handling the system's demands. Let's take a closer look at pressure drop through valves and fittings. The key formula here is delta P equals K times rho times V squared divided by 2. Essentially, this tells us that the pressure loss depends on a few factors: the flow velocity, the fluid density, and a coefficient K that varies depending on the fitting or valve. For example, if we consider an elbow fitting with a K value of 0.9 and a flow velocity of 2 meters per second, the pressure drop, or delta P, is approximately 0.3 meters of head. This illustrates how even small fittings can contribute to overall system pressure losses. Understanding these pressure drops is crucial because they impact flow efficiency and system performance. By accounting for them early in our design, we can ensure smoother operation and optimize energy use across the entire system. Let's take a closer look at pipe sizing for water supply and drainage. As you can see, the key formula here is Q equals A times V. This means that the flow rate, or Q, depends on the cross-sectional area of the pipe and the velocity of the water. It's important to also consider the drain slope, which should typically be between 1 and 2%. This slope ensures proper drainage without causing issues like blockages or backflow. For a practical example, imagine using a 20 diameter pipe with a flow velocity of about 1 meter per second. That setup results in a flow rate of approximately 1.26 liters per second. Understanding these principles helps us design efficient piping systems that handle the expected flow smoothly and reliably. This ties into the overall theme of creating safe, effective water supply and drainage solutions. Let's take a closer look at the firefighting system design, which is guided by standards like NFPA 13, 14, 20, 22, 25, 72, and 2001. These standards help us ensure that our fire protection systems are reliable and effective. Now, one of the key aspects is understanding the formulas used to calculate system parameters. The first formula is for the head, H, which accounts for several factors: the pressure, the weight of the water due to gravity, friction losses, and fittings or other losses. Specifically, H equals the sum of pressure, rho for the water's weight, HF for friction head loss, and the sum of K values for fittings or valves, all divided by the specific weight of water, gamma. This helps us determine the pressure head needed at various points in the system. The second formula is for flow rate, Q, which is proportional to the square root of pressure divided by a constant K. This relationship highlights that as pressure increases, flow rate also increases, but at a diminishing rate. Let's look at an example. If we need a flow of 500 gallons per minute, and we're working with a head of 100 feet, the power required is roughly around 25 horsepower. This gives us a practical sense of the energy needed to operate the system efficiently. Overall, these formulas and standards are critical. They connect to the broader goal of designing fire safety systems that are both effective and compliant, ensuring safety for all building occupants. Now, let's look at how we integrate BOQ from the calculated results. The key formula here is quite straightforward. QTY equals the sum of length times diameter for all items. So, essentially, we're adding up the quantities based on the physical measurements. Then, to determine the cost, we multiply the total quantity by the rate, and importantly, we add a 10% overhead to cover indirect expenses. For example, if we have a pipe length of 220 meters with a 2-inch diameter, the estimated cost would be around 12,000 SAR. This method allows us to accurately translate our measurements into financial figures, which is crucial for budgeting and planning. It ties back to our overall goal of ensuring precise and efficient project cost management. Let's take a closer look at this HVAC equipment schedule example. As you can see, it provides a clear way to specify the different pieces of equipment used in a system. For instance, the example lists an AHU, or air handling unit, with a capacity of 12,000 CFM, which stands for cubic feet per minute, at 35 tons of refrigeration. This tells us how much air it can handle and its cooling capacity. Similarly, the FCU, or fan coil unit, is shown with a capacity of 600 CFM and 1.5 tons of refrigeration. The key point here is that these schedules help us document the specific equipment, including their airflow and cooling capabilities, which are critical for system design and troubleshooting. By breaking down the equipment this way, it allows us to quickly understand the scope and capacity of each component in the HVAC system. This example ties into the overall theme of properly planning and documenting HVAC systems for efficiency and performance. It's all about having a clear, organized way to communicate what equipment is installed and its specifications. Now, let's wrap things up with some key points on coordination and the final summary. Throughout this presentation, we've seen how important it is to adhere to established codes and standards like ASHRAE 90.1, SMACNA, NFPA series, SBC 501, IPC, and AWWA. These guidelines ensure our designs are safe, efficient, and compliant. For example, when checking electrical loads versus pump power, it's crucial to maintain a safe margin, typically around 15%, to account for unforeseen variations. This kind of coordination helps prevent issues down the line and keeps our systems running smoothly. Remember, the main goal is to integrate these codes seamlessly into our project planning and execution, creating a cohesive and safe environment. Thanks to this approach, we can confidently deliver reliable, compliant, and optimized solutions.